And now we're to angular momentum. Yay! It's just like regular momentum, but, you know, in a circle. I feel like a really lame DJ at a really, really boring nightclub. All right, guys, it's time for the physics of rolling motion. Okay, so basically, it's the same thing as linear momentum, except for reasons that just are unbelievable. Eventually, here in a minute, your book is going to define angular momentum as, wait for it, hold on, angular momentum as L. Where did it go? Angular momentum as L. Yeah, L. They define it as L. It's like, wouldn't linear momentum be L? And then, like, angular momentum be something else? To be fair, the statics textbook calls angular momentum H. So I think we're just running out of letters. So I'm going to not even bother with letters because I think these are all garbage and you just need to know what's physically going on. But basically, we're going to talk about angles. It's going to be awesome. Things move in circles. Rolling motion. First of all, rolling motion without slipping. This is complicated and it's not as easy as this picture shows. It can be worse, but in general, okay. This is a good point to make. Imagine you have a wheel on the ground and it's going like this. Okay, now watch the center of the circle as it rolls. Roll, 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 roll. What did the center of the circle do? It went meow, 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 meow. Right? The center of the circle, in theory, went in a straight line. Okay. Now, for reasons way beyond the scope of this course, every time the wheel rolls a little bit more, this part down here is called the instantaneous, hold on, I missed a whole tan. Instantaneous center of zero velocity. So in theory, at every time that the wheel is rolling without slipping, this little point on the ground has no velocity. Okay, and so the farther away you get from that instantaneous center of zero velocity, the faster the points have to go to get around. So, for example, this point here has to go like this fast, but this point has to go twice as fast. Make sense? To keep going around in circles. And I don't think your book is going to get into this, but they all actually, each individual point moves at a direction that is perpendicular to the radius and the angular acceleration. But basically, I think what your book is getting to, and if this doesn't make any sense to you, don't worry about it. But remember, this is going forward. If you don't like the way that these arrows look, picture this ball rolling forward. So all the arrows have to be going somewhat forward in some kind of way. But based on what we had in chapter 10, we can say that the velocity of a particular point is given by the radius times the omega around that instantaneous center of zero velocity. And I'm doing so much hand waving, it's making me kind of sad. So if I look at the velocity of the center of a wheel, it's omega times the radius of the wheel. Similarly, I think I can say, that the tangential acceleration of the center, and in fact, the center doesn't move up and down, right? The center just goes straight. So there's no uppy downy acceleration to the center at all. The acceleration of the center is just straight up alpha r. And there's so much more math here. It's just mind-boggling. For the moment, I just want you to go like, okay, cool, thanks. I'm just going to accept this and move on. And if you really want, there's like whole entire videos and dynamics where we like get into the physics and the mechanics and we do calculus and it's so fun. But for the purposes of right now, the center of a wheel, if you get it, goes omega r, and the center of the wheel goes alpha r for its acceleration. Now, it's not true that the acceleration of this point does weird things, like alpha r or with a different r. We're not even getting into that. That's like a whole other life ahead of you. But it is okay to say that the velocity of this point up here is twice the radius times omega, right? Because it's twice as far away. So in theory, I could find the velocity of any of these points by just using geometry and figuring out, like, the velocity of this dude is just, velocity of dude is omega times d. And it goes in the direction perpendicular to that radial line going from where the ball or the wheel or wherever touches the ground, assuming that it's not slipping. Okay, so all that said, also the distance that the ball goes or the center goes is the distance that the center goes, oops, that's not what I meant. The distance that the center goes is theta r. So if it goes around, if you think about it, if it goes around like a full length of the circle and the circle like unravels itself and it's like, like if you pretend that like this part of the circle is this part of the circle and this part of the circle is this part of the circle and this part of the circle is this part. Does that kind of make sense? Like you're flattening out the circle. Then the center of the circle has gone the length of the circumference of the circle. So the distance is 2 pi r if it goes a full 2 pi in a rotation. So if it doesn't go the full 2 pi in the rotation, it's just theta r. So if it does whatever theta it goes through in the rotation, again, if you're measuring in radians, that's the distance that center point has gone. And hopefully that's something that you totally put into your brain for later. And that's what this is talking about. A cylinder rolls without slipping. Here, I'm just going to let you look through this in a little bit. What I'm really interested in is looking at this thing right here because they just threw it out here. And if you skipped the second half of chapter 10, you're going to have no idea what this is going on to be. So a quick aside on what this means. Just like we have F equals mass times acceleration. Okay, that goes lefty, righty, uppy, downy. A way to think about mass is a resistance to linear acceleration. Okay, so the more massive you are, the harder it is to change your speed. Okay, now there's this other thing called a moment, called I center mass alpha. Okay, and this is the roundy version of it. So this is a torque, so like torque, like how hard is it to torque something? How difficult is it to get things to turn? And so there's this property of material, and it's called the mass moment of inertia, or mass moment of inertia. I'm thinking of something else. Mass moment of inertia, which is its resistance to angular acceleration. Okay? So basically the idea is, and again, if you skip the second half of chapter 10, you missed it. The more mass I have away from the center, the harder it is to get something to rotate. So you might think that like something shaped like this is a lot easier to rotate than something shaped like, this, and centering it around that, right? So if the mass is here, if I'm trying to rotate all of this around, this center part, even if it's the mass is the same, and you just probably can hopefully get this kind of intuitively because we could prove it with math and calculus, but I don't think anybody wants that right now. And if you do, there's other videos that I have that do that. But basically the idea is when the mass is far away from the center, it's harder to get it to start to rotate. Whereas if the mass is more concentrated toward the center, so even if these weigh the same, so if the mass of this is 10 and the mass of this is 10, it could be that the IC of this is like, 50, but the IC, and I'm calling it IC, I think your book calls it the center of mass. Center of mass might be like 400, just because there's so much more mass that you have to get around to get it to spin. Okay, so basically the idea is we're looking at torque, which we only have marginally talked about, basically saying that the way that the mass is distributed around an object, the harder it is to get it to rotate. And that makes things pretty crazy. The good news is that you can actually look up these instantaneous, or these mass moments of inertia in a table. So that's definitely something that we'll need to look at separately. But I just kind of wanted to do a top level look at this right now and see if there's anything else that we need to specifically define before we get way into the math. No, we're just doing F equals ma and conservation of energy. And okay, so we could do it just like you have 1/2 mv squared. Whenever things are rolling, you also have 1/2 I omega squared. So basically the idea is you have the kinetic energy for translation, and you have the kinetic energy for rotation. So we're really kind of going way off the rails here, and introducing a whole, so how before I was like, oh look, we have this 1/2 alpha t squared plus omega t plus theta naught. Isn't that cute? Look how everything's related. Well, it turns out that we have these analogs to kinetic energy and linear momentum and angular momentum all have these relationships that basically means that once you know that mass is basically like mass moment of inertia, and that velocity is basically omega, and eventually you're going to get something that's like, so you know how linear momentum was mv, right? Well, you can do, let me see, I want to make sure I get this right. Linear momentum is r cross momentum, which is basically like the spinniness. So you have momentum, and you also have the spinniness of the momentum. Oops. So how much does the momentum spin around? So you have here, the momentum's going lefty right, up and down. And now here's your oh, but also the moment is also causing it to spin, so there's all these really interesting concepts. So I just kind of wanted to get your brain open to those ideas. Let's see, we have angular momentum. Is there anything else that I'm specifically going to look at here in a second? Angular momentum, and what is 11.3? Conservation of angular momentum. So just like you have conservation of linear momentum, you have conservation of angular momentum. So once you get something spinning, it's going to stay spinning until, there's an external, we call it a moment, an external torque acting on it. Until you get in there and you say, no, stop spinning, it's going to keep spinning. Just like if something is going lefty-righty, it's going to keep going lefty-righty until you say, no, stop. So basically, this is super straightforward. And straightforward is Professor talk for, please don't ask me any questions. No, that's not true. You can ask me questions. Super straightforward, but we say that it's straightforward to intimidate you so you don't ask questions and we don't have to try to explain it. Oh no, I gave away the secret. But yeah, so basically everything that we've done, lefty, righty, uppy, downy, and we spent weeks and weeks and weeks and weeks doing, now we're going to do roundy, roundy in a day and a half. So that's going to be fun.